few announcements. So we have the midterm rooms scheduled. So you guys, half of you guys will be in this room. The other half will be in Solus 104. I'll put up some maps next lecture so you get a better idea of what Solus is. Just find your room based on your last name. This will give you guys a little more room to spread out. We'll be at about 50% of capacity. Any questions? Any logistics questions? I'll send this out by email as well. So you have it.
Is it comprehensive or multiple choice?
The question was, is the exam comprehensive or multiple choice? It's not multiple choice. There'll be a practice exam that you guys will get later this week. It should give you a fairly good idea of what the exam will look like. And on Monday, I'll actually, in lecture, do a little bit of a review. And the TAs are putting together review sessions as well for early next week.
I just have a hard time writing.
So let's continue our discussion on mathematical algorithms. We'll finish this up pretty quickly and then move on to the grades. Excuse me, guys. Can you stop talking? Okay. So last time we left off with iterative methods. You guys saw how to take the roots of functions using the Newton-Raphson algorithm. We'll finish up our discussion of Newton-Raphson today. And then we'll talk about taking a square root of a floating point number. So in previous lectures, you saw how to take the square root of an integer, either take the ceiling or the floor of a square root. Today we'll talk about how to do that with floating point numbers. And then finally, we'll briefly talk about a method for approximating pi, just as another example of an iterative method. So let's go back to where we left off last time. We wanted to find the roots of x squared minus 3 using an iterative method. And so let's take a look at what the code looks like. So again, we define a macro with a maximum number of iterations here at 20. Go into our program here. We declare a set of variables, x, f of x, the derivative of f evaluated at x, and a bookkeeping variable I. We ask the user for an initial point. Remember with Newton-Raphson, you have to start with an initial guess for your loop. Take that in from the user. We start at the for loop, and so this for loop is counting from 0 to num iterations minus 1. Once I hits num iterations, we'll fix it. So there's a maximum number of loops that we can have here. At the beginning of the loop, we calculate f of x for our current guess of the root. So simply evaluate the function. Then we calculate the value of the derivative of f at x. And obviously the derivative of x squared minus 9 is just 2 times x. We check to make sure that that derivative value is not we check to see if it's equal to 0. If that's the case, we have to break out of our loop early because we don't want to hit this divide by 0 error. Right? If it's not equal to 0, we can calculate the next iterative step in Raphson. If you remember, to calculate that, we just take our previous guess, x, and subtract off the ratio of x and the value of the derivative of f at x. At each step, we're printing out the value of our next guess. So here it's just x of I, where I is the iteration step, is equal to our current guess. And then finally, after we exit the loop, we'll print out the final approximation of the root x. And that's it. We can return 0. Great. Any questions about this program before we go? Okay, this should be a review from last time. So, a question you might be having right now is do I need to write a different program for every function that I want to evaluate roots for, right? So it turns out right now, given your current knowledge of C, that would be the approach that you take. Later in this class, we'll be talking about functions and pointers to functions. Some of you that have programmed before might be familiar with the way that you might define a function. But we'll go over that together in future lectures. And this will provide us with a way to write a more general form of the Newton-Raphson algorithm, where we can just swap out the function calls that it makes to deal with different equations that we're only calculating. So later you'll learn how to make these systems a bit more flexible. Okay. So let's turn to square root. So how do we calculate the square root of a floating point number, in this case a? So obviously, if we have a square root, we can rewrite the square root as a simple equation, right? So x squared equals a by just squaring both sides, and then we can write out x squared minus a equals 0, right? So here we have an equation where we can solve for the roots. So we can turn this into f of x, take a look at the derivative, and go ahead and use Newton-Raphson to estimate the square root iteratively. Now, there are other ways to do this, but this is a fairly straightforward way from the tools we've shown in this lecture. So here's an example where we're putting it all together, where we're asking the user for a number that they'd like to take the square root of. We're defining the maximum number of iterations, here 20, and at each iteration step, we're calculating f of x as x squared minus a, the derivative, and testing our zero condition and updating and so on. So is this very clear? So one thing to keep in mind is that algorithms like Newton-Raphson are successive approximations, right? And the solutions are called iterative solutions. So we're going to see in the next slide, you'll see another example of an iterative solution. So here, we're going to talk about the Archimedes pi approximation. So this is a way to approximate pi, obviously, and to developed by both Archimedes and formalized by mathematician Fact. So the way that they're approximating pi is using very simple relations that you'll be familiar with, which is that the perimeter of a circle has a pretty strict relationship to pi. And what they're going to do is they're going to take a look at the perimeter here. So here we're setting r to 1/2, right? So if we set r to 1/2, then the perimeter of this particular circle is pi, right? So what we'll do to approximate pi is we'll consider two additional shapes other than the circle. One is the perimeter of an n-gon. An n-gon is just a polygon with n sides that is circumscribed by the circle. So that just means that the circle touches all of the vertices here of the n-gon. We'll consider a second n-gon that is circumscribing. So that means that it surrounds the circle, and that the circle touches the center of the edges of each side of this n-gon. And if you look at this visually, you should be able to see a fairly simple relationship, right? So if the circumscribed n-gon perimeter is n, and the circumscribed n-gon's perimeter is n, we can set up an inequality here. We know that for all n, right, the circumscribed n-gon has to have a smaller perimeter than the circle, and the circumscribing n-gon has a larger perimeter than the circle. And so that's an inequality for approximating pi. And as n increases, our approximation improves. So as we increase the number of sides in our n-gon, we're getting a better and better approximation of pi. So you should be able to see that visually, because as you increase the number of sides and you, as you go to infinity, you're going to get a shape that looks like a circle. And the circumscribed and circumscribing are going to become closer to one another in terms of size, and eventually at infinity overlap. So how do we take advantage of this inequality? Well, we need to set up an iteration that allows us to calculate successive approximations or successive values for these perimeters, for these known perimeters. So we start off with an initial condition, and that initial condition is a very simple n-gon. It's actually just a square, right, when we have 4 sides. And so we can go ahead and take a look at this particular case where we have a square that encases our circle and a square that is surrounded by the circle. And it should be fairly straightforward to go ahead and calculate the perimeters of each of these squares. We won't go through that in detail, but obviously the perimeter of A4 here is 2 times the square root of 2. And the perimeter of the larger square here is just 4, right? Each side is going to be 1. So with these initial conditions, we have an initial guess, right, as to what pi is. It's somewhere between 2 times root 2 and 4. Right? That should be true. But that's a really poor approximation, a very poor range. So we want to iterate off of this initial condition to refine our guess. And so the way we can do that is by looking at the relationship between A4 and A8 and B4 and B8. And we'll be able to set up a recurrence condition that connects these 2 conditions, right? And again, we won't go through all the trigonometry here. I'll just give you the solution. And don't worry about the trig if you're not comfortable with it. It's not the core material of this class. Here I'm just showing you an example of an algorithm, of a very effective algorithm. So it turns out that we can calculate B2n by using an and bn. And again, if you go through the trigonometry, you'll be able to calculate out these relationships. And similarly, we can calculate A2n from an and B2n. So what this means is that we have a recurrence here, right? We have an initial condition of B4 that we calculated, and we know how to calculate successive approximations of 2 times n, right? So here we know what the foregone or the square solutions look like, and here we can go to the octagon and then go to 16 sides and so on and so forth. Is that pretty clear in terms of the approach? Again, don't worry about the trig. You can figure that out on your own time if you're interested, or you can talk to me in office hours. So the basic program to do that is pretty straightforward, and here I'll just pop up the whole program. So what we're doing in this program is we're setting up our iteration. We set up our initial condition here. We know that b was initially equal to 4. We can use the method that I showed you earlier for calculating square roots to come up with an initial setting for a, because that was 2 times root 2. And so here we're just solving for that. Right, so here we're solving for root 2, finding the roots of x squared minus 2. And then we'll just multiply that by 2. So now a is set to 2 times root 2. We print out that initial setting of a, and then we iterate. And we iterate for pi iterations here, which we've defined as 30. And in each iteration, we use that recurrence relationship to calculate our successive a's and b's. Right? Is that pretty straightforward? Great. And so finally, what we can do here is once we get down here, we can set a equal to x, right? And print out our current values for a and b. So what's happening here again, with each iteration, we're applying those equations. If you want later on, you can go back to the two slides and compare here. So here, again, for a times 2n, we needed the square root of an b times 2n. And so we can again use our root finding methods to calculate that, right? So here we're just setting b equal to the relationship in the previous slide, and we're using root finding to solve that second equation. By setting a equal to our root estimate and printing out.
Oh, you need to memorize these algorithms for the midterm?
No, I don't expect you to memorize this pi algorithm for the midterm. These are meant to be examples. Now, these general types of problem solving, you should become familiar with, and you should understand why these solutions work. So, again, here we're calculating A4 using our root finding. This gives us square root of 2. This is the number of iterations we use for that initial, for calculating square roots. Here we're calculating a times 2n. Again, using our square root finding algorithm. And now we have our number of iterations that we're using to solve for pi. Right? So again, this type of code becomes much simpler once we will introduce functions. If you'll note, there's a lot of replication in this code. We're using Newton-Raphson twice. And once you can define your own functions, you'll be able to replicate this functionality with one block of code. And you'll just be calling that block of code again and again. Great. Any questions about the mathematical algorithms we went over? If not, let's move on to talking about arrays. So, basic outline for the next few lectures. Again, we'll keep going through this content until Friday, and then on Monday I'll do a review lecture. Wednesday is obviously the exam, and we'll pick up with this material again on Friday, on next Friday. So, basic outline, I'm going to introduce arrays, provide you with some simple examples of how you can use arrays, show you some slightly more complicated mathematical examples, and then we'll talk about string arrays. So far, you've used some string arrays when you've been printing out strings with printf, but you haven't been manipulating string arrays, which will give you powerful ways to process text in your programs. And then finally, we'll talk about two-dimensional arrays, which these basic concepts can also be applied to three-dimensional arrays. Two-dimensional and three-dimensional arrays become very important for fields like image processing or video processing. An image is essentially a two-dimensional array. Each pixel is an element in that two-dimensional array. And a video is, you can think of it as a three-dimensional array, right? You just have time on top, a sequence of those two-dimensional images. So let's dive in here and introduce arrays. So why do we need arrays, right? Let's look at an example task where an array becomes very useful. So let's say we have a company that has 800 employees, and they want to read their salaries, compute the average, and determine how many salaries are above the average, right? So you'll note that first we need to determine the average, then we need to look at the number of salaries that are above it. So we need to go over the numbers twice, right? So in the past, you've created programs, or you've looked at programs that can take averages without arrays. And there we were taking in the numbers as sequential inputs. adding them together, and then dividing them by the total number of inputs, right? But if we need to do a second pass on the data, we obviously wouldn't want the user to have to enter the numbers in again. Right? So, one way we could have solved this is perhaps by declaring 800 individual variables, which would be incredibly cumbersome and kind of defeats the whole purpose of programming, which is to make things more convenient and automated. So obviously typing in 800 names in addition to values, not a great idea. It also means that the compiler would have to keep track of these 800 names. And on top of it, you can't easily loop over this data, right? There isn't a way to index over these different names, these different name variables. So the solution to all of these problems is arrays, right? And so what are arrays? They're just ordered lists of variables of the same type. So they basically look something like this. So here is just a graphic of an integer array. It's just a set of memory location with these variables of the same type. And how do we declare them? So this is an example of some new C syntax. So unlike the last set of lectures, you're going to be learning some new concepts here in C, as well as some new syntax. So if we wanted to declare an array that can hold 800 salaries, here it's a double type. So now we have 800 doubles in the array called salaries. And then how do we access the elements of the array? Well, once the array is declared, then in code you can use the elements of the array like you would any other variable, except you have to access the particular element of the array to use it. And here you provide the simple indexing notation. So we'll talk about this a little more, but arrays start at index 0 and go up to n-1. So to access the first element of the salary array, you can use an index of 0. You can also use expressions as indexes, which will obviously be very useful if you want to loop over an array. So if you wanted to loop over an array with a for loop with a bookkeeping variable I, this would allow you to access the type entry of salaries. And those expressions can be more complicated as well. C will go ahead and calculate the value of this expression, and that value will be indexed into the array. So a couple of comments. So here we've declared an n-element array, right? So again, the notation is the data type, the name of the array, and the number of elements in the array. Again, the first element in the array has index 0, and the last element of the array has index n-1. And so we're going from 0 to n-1. That's n total indices. And so let's take a look at an example of an array. So here's just an integer array that takes in 4 values. And let's say these values are written into the array, 124 and 5 and so on. To access 124, we would index my and m at 0. To access the second element, my and m 1, 2, and 3. And that's how you access all 4 elements. Now, an important note about what arrays look like in memory is that they're always consecutive memory cells. This will come up a little later in this class when we talk about memory allocation and pointers. But just keep in mind that when you declare an array like this, physically in memory, it's a block of cells that are contiguous. Any questions?
Could there be two-dimensional arrays?
Yes. So we'll talk about two-dimensional arrays in later lectures, either later this week or after the midterm. So you saw how to declare an array. How do we assign values? So when you declare an array like I showed you in the previous slide, much like other variables, the arrays are going to have arbitrary initial values, right? Unless you initialize the elements of the array, the numbers that you get back, for example, an integer array, will just be based on what was generated before you declare that array. So it's important to initialize and assign values to your array. So one common way to do that is assignment using a loop. So here's a for loop. Let's say we declared salaries as an 800 element array. Here we're just looping from 0 to 799, all of the indexes in the array, all of the locations in the array, and we're just setting a value. And here we're just initializing the value based on the index number for no particular reason. We could put in any value here to initialize it, right? Obviously, for that salaries program, we wanted to take in user input. So you could have loops, and at each loop, taking in a user input of the salary. And again, this for loop is going to loop from 0 to 799, which is all of the indices of the array. So it turns out there's a more convenient way to initialize an array. Whenever you have a fixed size array, and we'll return to this concept of fixed size. So far you've only seen fixed size arrays. These are arrays where you've explicitly told the program how many cells there should be before compiling. You put in a constant number in your declaration, right? So when you have a constant here and the array is fixed size, you can initialize just by using this curly bracket notation, right? So open curly bracket, and then for this double array, one double constant for each element in the array, right? So here's another example. So in both of these examples, we have the same number of elements in the curly brackets as our declaration. But it turns out that you don't have to follow that rule. If you provide less values, the missing values will be automatically filled with zeros, which is very convenient. So, for example, if we declare and initialize grades in the following format, we'll find that these two lines of code are equivalent, because C will automatically fill in the two missing spots with 0 here. Is that clear? So,
did you say you could just put two curly braces and it would initialize all to 0? Or no?
Yeah, so you could just put a single 0 in there, or curly brackets, I believe work. I'm actually not sure, just test that out off the top of my head. So you can determine array size from initialization. So for example, we can write the following notation, where you don't provide a number here within our square brackets. You simply declare grades as an array, and you initialize it. And C will automatically count the number of elements here, make grades that size array, and obviously assign these values. So all three of these lines of code are functionally equivalent. However, this example would obviously be different, right? Because, again, C needs to use the initialization to decide how big the grades array is. So this will be a 5-element array, and this declaration and initialization will result in a 3-element array.
Can you define a constant at the beginning, or define something at the beginning, like this name is size, and then put it inside of the square brackets?
Yeah, so the question was, could you declare
Declare,
something
yeah.
that's a size and put that in the square brackets? So in the next slide, we'll talk about how you can use variables at declaration.
Okay.
And to return to, I think I answered your question earlier about initialization. So I think you were asking about this scenario, which is where you can put in empty curly brackets, and this would be used to initialize the array. So these two are different, right? Whereas this notation would result in all zeros in your array. So this is actually a very handy way to declare and initialize your array, because it, with this line of code, you know exactly what's in your array. It's going to be all zeros. Whereas here, if you just declare the array, you're going to have arbitrary values sitting in the array.
The first three-size array of double prices, if you put in more than 3 values, would it just only recognize the first 3 values?
So I believe that will create a compiler error.
Okay.
So again, this is uninitialized. So a question that was just asked.
Can you change the array size after it's declared?
No, the array sizes, so the question was, can you change array sizes once they're declared? No, they're fixed once they're declared. So a typical strategy that people use is to declare the maximum size array that they would need, and then to keep track of, let's say you are going to have a variable number of elements in your array. Always declare larger than what you think you need, and then keep it another variable that tells you how many elements you're using in your array. Okay. So it turns out that you can declare an array whose size is determined at runtime. So you can define the size of an array based on other variables in the code. So for example, if we take in a user input array size, we can then use that in the code to define the size of the array. But once that array is defined, its size stays fixed, right? From there on in the code. So one caveat when you use these runtime style declarations, and again the difference between this declaration and the previous declaration, is here the size is decided by a variable. So every time you run the program, you get a different size array. Whereas in the previous examples, we were using a constant. So every time when you have a constant for the array size, obviously every time you run the program, you're going to get the exact same size array. And because of this difference, when you use runtime array declarations, it turns out that you cannot, you can't initialize the array of declaration. So you can't use this notation for these runtime declared arrays. And the reason for that is C doesn't explicitly know how big this array is going to be. So this notation won't work. However, you can initialize the values later. And so if you are using this type of runtime declaration, a common strategy is after declaration to use a for loop to set the values of the array. Any further questions about the basic syntax of array declaration and assignment? So we'll move on then to talk about some simple examples of using arrays. So let's go back to our salary problem. Again, what we wanted to do was calculate the average of 800 salaries and then count the number of salaries that are above the average. So let's look at that program. So again, we're using a macro definition here to set the number of employees to 800. We start our main loop, and so in our main loop, we're declaring an array variable that's the size of that is num employees, or 800. We're declaring and initializing a variable sum and a variable average, and then we're going to have a bookkeeping variable I and a count of the number of variables that are above, or the number of salaries that are above the average. To populate the array, we'll use a for loop, and in that for loop, we'll just take in a user input, which will be the salaries. Again, this is a short program, so it can fit on the slide. If you were to actually write up this program, you'd want to provide a better user interface. Here we're not even telling the user what the program does, but the code logic is still correct. So here, at each we're setting an element of the array, and then we're adding that input salary to sum. Once we're done iterating over 800 entries, we take the average, which is obviously just the sum divided by the number of employees. And then we need to go back through the array to see how many of those elements are above average, right? How many of those salaries are above the average. And again, we do that by looking from 0 to 799, or 0 to 991. And for each array element, we're checking if the salary is greater than the average. And if it's greater, we add 1 to above average, right? So this logical expression will evaluate to 0 or 1, obviously, right? And so if the salary is above, we'll add 1. If the salary is equal or below average, we'll add 0. And again, we're accessing each one of the array entries one by one.
So arrays could be are just used to like index the integer, double, whatever it is. But in terms of memory allocation, is it is it able to, for 800 integers or doubles, would it take up just as much as like 32 bits times 800, or?
So the question was, does it just take up 32 bits times 800? Yeah, approximately. That's how much it takes up. So it's going to allocate a block of memory that is 800 integers, and each integer is going to be 32 bits or 8 bytes. So it'll be 8 bytes times 800. Sorry, not 8 bytes. 4 bytes times 800. An integer is 4 bytes, or 32 bits. Okay.
It doesn't matter if you don't use all of the array, it's still going to use up the same amount.
Yeah, so the question was, if you don't use all of the array, will it still use the same amount of memory? And here I'm assuming by using the array, you mean writing a value into the element,
Yeah.
reading a value from the element. That's correct. So the size of the array is decided by this declaration, not by the usage of the array.
Okay.
Right? Obviously, when you write your program, you have to keep in mind how you're using the array. So, for example, if let's say in this for loop, we added a way for the user to exit, right? So maybe we could have added some logic so that if the user entered a negative salary, it would exit out of the for loop.